Here we're going to look at question 15 from section 2 of the ENGAA 2018 paper. In this question we're told we have a solid cube which has a total surface area of 96 centimetres squared. We're then told that we take this cube and we attach it to a spring and dangle it so that it's fully suspended by our spring, which is going to have a spring constant of 2 times 10 to the 4 newtons per metres. And at equilibrium we're told that the extension of our spring is going to be 1.6 times 10 to the minus 4 metres. After this, we take our block and we remove it from our spring and place it on a flat surface. The question asks us, what is the density of our cube and what is the pressure on our final flat surface? If you would like to have a go at this question yourself, then please pause the video now. Otherwise, let's have a go at doing it ourselves. So, to answer this question, we should go ahead and think about the variables which we're asked to find. So, first, we're asked to find the density of the cube. Now, what's the density of an object given by? Well, it's given by its mass divided by its volume. Then, if we think about the pressure that the cube is going to exert when placed on a flat surface, then this is going to be equal to the force that the cube supplies, its weight, divided by its base area, the area that the weight is distributed across. So, if we do go ahead and look at these, then we can probably tell that we can, for the volume and base area, we're going to need to find the length of one of the sides of our cube. So let's label it on as x for now, and we can work out what it's going to be when we get to it. But in the meantime, let's try and think about the mass of our cube, since we're going to need that for the density, and then we're going to need it to find the weight and the pressure. But how could we find this mass? Well, how about we go ahead and consider the situation with the spring up here. Now, if we think about this spring, then there's one law which we pretty much always have to use whenever we have springs, and that law is Hooke's law. So, what is Hooke's law? Well, it's that the force that a spring supplies is equal to the spring constant multiplied by the extension of the spring. So, luckily we're given the spring constant and the extension up here, so we just have to find the force which the cube is supplying to the spring. To work that out, how about we think about the forces actually acting on our box, or on our cube, sorry. So upwards we're going to have this force, F, and then downwards we're going to have the weight of the block. So the force F supplied by the spring, or produced by the spring, is going to be equal to this weight at equilibrium. Therefore, we can substitute this into our expression alongside our two values of the spring constant and extension to get the following. That mg is equal to 2 times 10 to the 4 multiplied by 1.6 times 10 to the minus 4. Then, of course, we can see that the 10 to the 4 and the 10 to the minus 4 are going to cancel out with one another, and if we divide by g, then we get that the mass is equal to 2 times 1.6 all divided by 10, taking g to be 10, which is just going to go ahead to become 0.32 kilograms. So the mass of our block is going to be 0.32 kilograms. So with this, we can go ahead and try and find our density. But to find our density, we're still going to need this volume, which, of course, we're going to require the side length of our cube for. So if we have a bit of a think, then we know the total surface area of our cube is this 96 centimetres squared. And if we were to find that algebraically using x, then we know that the area of one of the sides is going to be x squared. So the total area is going to be 6x squared. So we're going to have our 96 centimetres squared is equal to 6x squared. Then we can divide through by 6 to get that x squared is equal to 16, and then square rooting we get that x equals 4 centimetres. So our cube has a side length of 4 centimetres. Finally, we can now go ahead and actually calculate our density. So this density is going to be equal to the mass of our object, our 0.32 kilograms, which I've converted here to standard form. We're going to divide that by the volume of our cube, which is going to be this. So it's worth noting that the side length we've calculated is in centimetres, so we need to convert it into metres and then cube it to get the volume. So this is going to give us kilograms per metres cubed as our unit of density, which is what we're asked for in the question. So it's going to be much easier to convert as early on as possible rather than trying to change it later on. Now if we do go ahead and cube these two things in the bottom bracket, and simplify it a little bit, then we get that the density is equal to our 3.2 times 10 to the minus 1 kilograms divided by 6.4 times 10 to the minus 5 metres cubed. which we can just go ahead and cancel out our 3.2 and our 6.4 and our powers of 10 to get a density of 5 times 10 to the 3 kilograms per meters cubed. Now, if we want to move on and find the pressure, that our block produces against a flat surface, then we need to find the weight of the block. So this is just going to be the mass of the block multiplied by the gravitational field strength, G. And then we need to divide this by the area of the base, which is just going to be our side length of 4 centimetres, which again I've just converted into metres here, and that'll be squared to give us metres squared. So then going through and simplifying this a little bit by taking G to be 10, then this top part of the fraction becomes 3.2, and the bottom part, just by squaring what's inside the bracket, is going to become 1.6 times 10 to the minus 3, and then dividing and cancelling through our 3.2 and 1.6 and bringing our 10 up to the top, we get that the pressure produced by our block against the surface is going to be 2 times 10 to the 3 newtons per metres. So comparing this pressure and our density to the answers given in the question, we find that this is going to correspond with answer G.